Welcome back, everyone. Today we're diving into something really exciting. But before we get there, let's briefly talk about where we left off in our last episode. We explored BERT, which was all about deep bidirectional transformers for language understanding. BERT gave us incredible insights into how models can use the bidirectional context to comprehend text more effectively. It was a real game changer for classification and question answering, wasn't it?
Absolutely. I remember we compared BERT's bidirectional focus with GPT's unidirectional approach, where GPT worked so well for generative tasks.
Exactly. And that's where today's episode becomes even more fascinating. We're moving beyond the single-focused models like GPT and BERT to something that merges the best of both worlds, T5. Unlike GPT, which is a decoder-only model great for generation, and BERT, an encoder, only one for understanding, T5 takes a combined approach. It's an encoder-decoder setup that uses a unified text-to-text format for all tasks.
So, it's like T5 can both understand and generate text with the same efficiency?
Right on. The versatility of T5 lies in how it treats every NLP task, whether it's translation, summarization, or classification, as simply transforming text into text. This unified framework is what makes T5 stand out. Recently, T5 has been making waves in the NLP community, setting benchmarks in transfer learning and advancing areas like few-shot and zero-shot learning.
It sounds like T5 isn't just about having one model for many tasks, but also making the training process simpler and more scalable.
Precisely, and that's why it's been so influential not just in research but in industry as well. Its ability to handle diverse tasks effectively has made it a go-to for many practical applications.
So today, we're going to explore how they achieve that level of adaptability.
Yes. We'll dive into the details of how T5 was set up, how it leveraged a unified approach, and what made it achieve state-of-the-art results across multiple NLP benchmarks. We'll cover how the authors conducted a systematic study comparing different model architectures, objectives, and datasets. It's a real testament to how combining simplicity with power can yield incredible results.
I'm looking forward to understanding how they manage the unified text-to-text approach for such varied tasks.
Great! Let's get into it. We're starting with the abstract of the paper, where we'll unpack the core ideas and set the stage for understanding the model's impact and capabilities. Let's go! Today we're going to discuss the abstract of the paper titled Exploring the Limits of Transfer Learning with a Unified Text-to-Text Transformer. This abstract is packed with interesting insights about the effectiveness of transfer learning in natural language processing, or NLP. Let's break down the key elements and concepts presented in this part. The abstract begins by explaining that transfer learning involves pre-training a model on a data-rich task before fine-tuning it for another, often more specific task. It's an approach that has really taken off in NLP due to its effectiveness. Does anyone know why pre-training might be particularly advantageous for NLP tasks?
I think it's because language data is often diverse and large scale. So pre-training can help the model build a general understanding of text that can be useful for various tasks.
Exactly. Pre-training helps develop broad language skills that can be fine-tuned for more specific tasks, like sentiment analysis or summarization. In this paper, the authors propose a unified framework that can convert all sorts of language tasks into a text-to-text format. This means that regardless of whether the task is translation, summarization, or classification, it can be represented in the same format. Why do you think having a unified approach might be beneficial?
Maybe because it simplifies the system. If the model only needs to deal with one format, it can become more efficient in handling different tasks, right?
That's right. By unifying different NLP tasks into a single text-to-text format, it becomes possible to use the same model and methods for a wide variety of applications. This greatly reduces complexity and makes the model more versatile. The abstract also mentions that the authors conducted a systematic study where they compared different pre-training objectives, architectures, and datasets. They used a new dataset called the Colossal Clean-Crawled Corpus and managed to achieve state-of-the-art results across multiple benchmarks. Can anyone explain what we mean by state-of-the-art results?
State-of-the-art means achieving the best performance compared to other existing models or techniques on the same tasks.
Perfect. It means they pushed the boundaries of what was possible with transfer learning in NLP, achieving the highest accuracy and performance on benchmarks like summarization, question answering, and text classification. And, to encourage further research, they even released their dataset, pre-trained models, and code. Why might sharing these resources be important?
I guess sharing resources helps other researchers to build on their work, validate it, or use it for further advancements without starting from scratch.
Exactly. Sharing the dataset and models promotes collaboration and progress in the field, allowing others to test new ideas or improve upon the existing work. To conclude, this abstract sets the stage for a detailed exploration of how a unified approach to transfer learning, with a focus on scalability and dataset quality, can achieve remarkable results across many NLP tasks. It highlights the importance of systematic comparison in understanding what drives success in transfer learning, and emphasizes that innovation often comes not just from new methods, but from applying known methods in a more efficient or comprehensive way. All right, that wraps up our discussion on the abstract. It gives us a high-level view of what this paper aims to achieve and sets the context for the rest of the content. Let's move on to the introduction, where the authors lay the groundwork for their study. The introduction starts by addressing the challenges in NLP and the need for general-purpose language knowledge, often developed through pre-training. Who can explain why pre-training is so important in NLP?
Pre-training lets the model learn basic language structures before working on a specific task, like learning grammar before writing an essay.
Exactly. Pre-training gives the model foundational knowledge, such as words, grammar, and context, that helps it handle specialized tasks. The introduction distinguishes between different levels of this knowledge, like low-level, spelling, versus high-level, complex reasoning. Why might this distinction be important?
Different tasks need different levels of understanding. Simple tasks need basic knowledge, but complex tasks need deeper understanding.
Exactly. For tasks like spell checking, low-level knowledge is enough, but complex tasks need deeper comprehension. Pre-training helps with both levels by using vast amounts of unsupervised data, which is readily available online. The authors also discuss a shift from word embeddings to pre-training entire models with unsupervised methods. Can anyone recall why word embeddings were important in early NLP?
Word embeddings help represent words in a way that captured their relationships, making similar words have similar representations.
Correct. Word embeddings showed similarities between words, like cat and feline. Modern methods go further by pre-training full models, enabling deeper understanding of context and nuances. The introduction also emphasizes the importance of scaling in ULP, using more data and larger models for better performance. Why is scaling so important?
More data and larger models help capture complex language patterns, including idioms and rare word usage.
Exactly. Larger models with more data can understand nuanced language and adapt to different tasks. However, this also raises computational costs, which makes efficiency crucial. Finally, the authors propose a unified approach by treating every NLP problem as a text-to-text task. This makes training more consistent and scalable, enabling the same model to handle tasks like summarization, translation, and more. Consistency helps test and compare techniques effectively as the field evolves. That concludes the introduction. The authors clearly outline how NLP transfer learning has evolved, the benefits of a unified framework, and the challenges they are addressing, all of which sets the stage for the rest of the paper. Now that we've covered the introduction, let's move on to the setup. This section lays the foundation for the experiments, how the model was built, what tasks they used, and other key details to ensure the research is reproducible. The authors used a transformer model with an encoder-decoder architecture. Who can remind us why this setup is used?
It's for transforming one sequence into another, like translation.
Exactly. The encoder processes the input into a representation, and the decoder generates the output. This approach works well for tasks like translation or summarization, fitting their text-to-text framework. Next, they used a two-phase training process: pre-training for general language understanding and fine-tuning for specific tasks. Why do they separate these phases?
Pre-training gives a broad understanding, while fine-tuning specializes for specific tasks.
Exactly. Pre-training is like general education, while fine-tuning is specialized training. This allows the model to adapt better to specific tasks. They used the colossal clean-crawled corpus, C4, which was extensively cleaned to remove irrelevant content. Why is cleaning the dataset important?
To prevent the model from learning harmful or useless information.
Right. Quality data ensures the model learns useful language patterns without biases or irrelevant content. For evaluation, they used multiple downstream tasks like summarization, translation, and classification, as well as the GLUE benchmark. Why use so many tasks?
To make sure the model isn't just good at one type of problem, but has a broader understanding.
Correct. Testing on many tasks shows whether the model has a general understanding of language. They treated every task as a text-to-text task, where both input and output are text. Why might this consistency be helpful?
It simplifies training, as the model only needs to transform text, regardless of the task.
Absolutely. This unified approach makes the model adaptable across various NLP tasks, simplifying training and improving flexibility. Finally, they used a transformer with multiple layers balancing self-attention and feed-forward components. Why is balancing computational cost important?
Because training large models is expensive, so it must be powerful yet efficient.
Exactly. The authors balanced model complexity to achieve good performance without excessive costs. In conclusion, the setup clearly describes how the model, datasets, and training methods were chosen to ensure thorough and reproducible research, providing a strong foundation for their experiments and findings. Let's dive into the baseline section of the study, which plays a crucial role in evaluating their findings. The baseline provides a reference point, allowing us to see how any variations or improvements perform against a standard benchmark. It's like setting up a controlled experiment. You need a solid, consistent starting point to see if your modifications actually make things better. Let's break down the specifics of their baseline setup. First, the authors created a baseline model reflecting modern NLP practices. They chose a transformer model with an encoder-decoder architecture, much like what we've discussed before. This baseline model was built with around 220 million parameters. Why do you think they started with this model size?
I think it's because this size offers a good balance between performance and feasibility. If the model is too large, it could be expensive and slow to train, and if it's too small, it may not perform well.
Exactly. The authors needed a model that was powerful enough to perform well on various tasks, but still reasonable in terms of computational resources. Starting with a model that balances these two factors makes the baseline both effective and practical, helping establish a fair reference point without overwhelming computational costs. They used a two-phase training approach, pre-training and fine-tuning. We've talked about this approach before. Pre-training gives the model a broad understanding of language, while fine-tuning helps it specialize for specific tasks. What's notable here is how they conducted the pre-training phase. They used a denoising objective, which involves removing words from a sentence and training the model to predict the missing parts. Why do you think this approach might be more beneficial than simply predicting the next word in a sequence?
I think predicting missing words helps the model understand the context better. It has to know how all parts of the sentence fit together instead of just focusing on what comes next.
Exactly. Great insight. Predicting missing words forces the model to understand the broader context and relationships between all the words in a sentence, not just what comes immediately after. It helps the model develop a deeper understanding of sentence structure and meaning, which is especially important for complex language tasks that require contextual comprehension. They also trained the model using the colossal clean-crawled corpus, C4, a large and diverse dataset. They pre-trained the model for 524,288 steps, exposing it to roughly 34 billion tokens. The idea was to show the model a wide variety of text to help it learn different language patterns and contexts. Why do you think it's important for the model to see such a large number of tokens during training?
I think the more examples the model sees, the better it gets at understanding different contexts and language uses. It's like how people get better at a language the more they read and hear it.
Exactly. Exposure to a large data set helps the model learn the full range of language, from common phrases to rare and complex structures. By seeing billions of tokens, the model develops a nuanced understanding of language that makes it more effective across a range of NLP tasks. After pre-training, the model entered the fine-tuning phase. Here, the authors took the pre-trained model and adapted it to perform specific tasks such as summarization, translation, and question answering. They used a consistent learning rate and training steps for all tasks, ensuring that the process was uniform. Why might it be important to keep the fine-tuning setup consistent across different tasks?
Probably because if you change the fine-tuning setup for each task, it's hard to know if differences in performance are due to the model's ability or just different training methods. Keeping it consistent makes comparisons fair.
Exactly. By maintaining consistency and fine-tuning, the authors ensured that any differences in performance could be attributed to the model's capabilities and not to changes in the training process. This kind of fairness is crucial when evaluating improvements and comparing different configurations. They also compared this baseline model to a model trained from scratch for each specific task, without any pre-training. They found that models with pre-training significantly outperformed those trained from scratch, particularly in low data scenarios. Why do you think pre-training is especially helpful when there isn't much data available for a specific task?
Pre-training gives the model a lot of general language knowledge, so it doesn't need as much data to learn specific tasks. It's like starting with a good background knowledge instead of learning everything from the beginning.
Exactly, that's a great analogy. Pre-training acts like a foundation, providing the model with general language skills that make it easier to adapt to specific tasks, especially when there's limited data available. This head start is what makes transfer learning so powerful. It allows models to succeed even when labeled examples are scarce. To sum up, the baseline model set by the authors involved a transformer encoder-decoder architecture, pre-trained on a large dataset using a denoising objective. This provided a solid starting point for testing different modifications and improvements. Establishing this baseline is crucial. It means that any future enhancements can be compared clearly and reliably, giving us a true sense of whether new approaches are genuinely advancing the field. Moving forward, the researchers will use this baseline to explore how various changes, such as different model sizes, training objectives, or other tweaks affect performance. By grounding their study in a strong and well-defined baseline, they ensure that any progress they observe is meaningful and measurable, providing valuable insights into what works best in NLP. Let's move on to the sections about model architectures and unsupervised objectives. These parts of the study explore how changes in model design and training objectives impact performance, similar to testing different versions of a car to see what works best. The authors mainly used the transformer model, experimenting with different setups like encoder-only, decoder-only, and encoder-decoder. The encoder-decoder setup, which separates understanding from generating, works well for tasks like translation. Why might separating these functions be useful?
It allows each part to specialize. One focuses on understanding, and the other on generating.
Exactly. This specialization allows the encoder to fully understand the input, while the decoder focuses on producing accurate outputs. They also tested a prefix language model, which uses a shared transformer for both understanding and generating. How might this impact the model?
It could be more efficient but may lose some of the specialization of having separate parts.
Right. It's a trade-off. Using a single stack can reduce parameters and improve efficiency, but it may not be as specialized. They also tested parameter sharing between encoder and decoder, which saved resources but still performed well. Why might shared parameters work?
The same knowledge about language, like grammar, is useful for both understanding and generating.
Exactly. A lot of the linguistic knowledge is applicable to both tasks, making parameter sharing a good way to reduce model size without losing much performance. Moving on to unsupervised objectives, the authors experimented with various training approaches. One classic method was language modeling, where the model predicts the next word. They also used denoising, similar to BERT, where parts of the input are masked and the model reconstructs the original text. Why might denoising be better than predicting the next word?
It makes the model understand the whole context instead of just focusing on the next word.
Exactly. Denoising requires a deeper understanding of the entire sentence, which improves the model's comprehension of context. They also tried deshuffling, where the model had to reorder scrambled words, but it wasn't as effective. Why do you think that is?
It probably focuses too much on grammar and order without capturing deeper meaning or context.
Correct. Deshuffling mainly teaches structure but doesn't help as much with understanding the semantics, which is crucial for many language tasks. Overall, the denoising objective led to the best results, helping the model learn deeper representations of language. The encoder-decoder architecture paired with denoising proved to be the most effective, balancing efficiency and performance across a wide range of tasks. In conclusion, the authors tested different model architectures and training methods, finding that a combination of encoder-decoder and denoising objectives provided the best adaptability and efficiency for their unified NLP framework. This setup formed the foundation for their successful performance across various benchmarks. Let's continue with the next important sections, which cover the pre-training dataset and the training strategy. These two aspects are really critical for shaping how well the model learns and generalizes, so let's dive into what the authors did in these parts. First, let's talk about the pre-training dataset. The authors wanted to see how the quality and nature of the dataset used for pre-training would affect the model's performance. Remember, during pre-training, the model learns about language in general before we ask it to perform any specific tasks. The data it's trained on at this stage will influence what it understands and how well it can apply that knowledge later. So they used a dataset called the Colossal Clean Crawled Corpus, or C4 for short. This dataset is built from web pages and aims to provide a large, clean, and diverse collection of English text. Why do you think a large and diverse dataset would be essential for pre-training?
Probably because language is so varied. If the model only sees a narrow type of text, it might not learn to understand all the different ways people use language, like different styles or contexts.
Exactly right. Language can vary a lot depending on the context, whether it's a news article, a conversation, or even a piece of fiction. By pre-training on a large, diverse dataset, the model can learn a broader understanding of language that applies to many different tasks and situations. The authors used C.4 because it allowed them to expose the model to a wide range of language forms. Everything from formal writing to casual phrases you might find in blogs or online forums. They also did a lot of cleaning to make sure the dataset was as high quality as possible. They removed boilerplate texts, repeated phrases, offensive content, and anything that wasn't natural language, like code snippets. This cleaning helps prevent the model from learning patterns that are irrelevant or even harmful. Why might including low-quality or irrelevant content be problematic?
I think if the model learns from low-quality content, it might start generating low-quality responses or picking up bad habits, like using the wrong grammar or repeating useless phrases.
That's absolutely correct. If the model sees a lot of low-quality content, it might start replicating those patterns, which could degrade its performance across the tasks we care about. Cleaning the dataset helps ensure that what the model learns is relevant, useful, and applicable across different tasks. The authors also experimented with using different datasets to see how much the data source itself impacted results. They found that while having a large dataset is helpful, the quality of that data, like making sure it's clean and representative of natural language use, was key to getting the best performance. It's a great reminder that more data is not always better unless that data is good. Now let's move to 3.5 training strategy. This part is all about the details of how they trained their models, and they made several strategic decisions that influenced the outcomes. They experimented with different ways of leveraging the pre-training and fine-tuning phases to maximize the model's ability to perform well on various tasks. Let's break down some of these strategies. One major strategy they explored was how to mix pre-training with fine-tuning. Typically, after pre-training is completed, a model is then fine-tuned on specific tasks separately. However, the authors tried a few variations here. For example, they compared the effect of multitask fine-tuning, where the model is trained on all downstream tasks at the same time, versus individual fine-tuning, where each task is learned one by one. Can anyone think of the advantage of multitask fine-tuning?
I guess if the model is trained on multiple tasks at once, It might learn things that are useful for all of them, like general skills that it can apply everywhere.
Exactly, that's a really good point. Multitask fine-tuning allows the model to transfer what it learns across tasks, meaning it can develop a more general understanding that helps with a variety of problems. For example, understanding sentence structure is important for both translation and summarization, so learning these tasks together might reinforce these skills better. However, multitask fine-tuning also has some potential challenges, such as task interference. If the tasks are very different from each other, the model might struggle to balance them, leading to suboptimal performance. This is why, in some cases, fine-tuning on each task individually, after multitask learning, is used to further polish the model for that specific application. They also looked into adaptive fine-tuning, which involves using a general pre-trained model and then continuing the pre-training but with data more similar to the specific task they care about. For instance, if the final goal is question answering, they might continue pre-training the model with similar texts before fine-tuning on the actual question-answer dataset. Why do you think this approach might be beneficial?
It sounds like it helps the model narrow its focus, like it first learns everything about language in general and then starts focusing on examples that are closer to what it's ultimately going to do.
Exactly, it helps bridge the gap between broad general knowledge and specific expertise. The model first gets a strong foundation from pre-training, and adaptive fine-tuning helps it focus on the particular nuances that are important for the target task. This additional phase makes it easier for the model to adapt and perform better on that final step. Finally, they adjusted the learning rates during fine-tuning to see how different settings affected the outcome. They found that keeping a lower learning rate generally helped maintain the knowledge gained during pre-training, while still adapting effectively to new tasks. Think of it like taking smaller steps when you're close to your goal so you don't accidentally overshoot and lose your way. In machine learning, a smaller learning rate allows the model to make more precise adjustments, which is especially important when fine-tuning, so it doesn't forget the broad knowledge it acquired. To conclude, the authors emphasized that both the quality of the pre-training data and the strategy for training are critical factors that significantly influence the model's final performance. A well-designed pre-training dataset gives the model a solid foundation, while an effective training strategy, whether it's multitask learning, adaptive fine-tuning, or carefully managing learning rates, helps polish and refine that knowledge to excel in specific applications. These sections are a great reminder that building an effective NLP model is not just about having a big model or lots of data. It's also about thoughtful preparation and strategic decisions throughout the training process. Each step contributes to building a model that is adaptable, efficient, and capable of handling a wide variety of language tasks with precision. Let's discuss scaling and the results. An exciting part of the paper where the authors push the model's limits to see what's possible by scaling up. Think of scaling as enhancing the model's capacity, making it larger and providing it with more computational power to see how much performance can improve. In 3.6 scaling, they experimented with increasing the number of parameters, which means adding more layers or making the layers wider. This allows the model to learn more complex language features, like adding more sophisticated parts to an engine to boost its performance. Why might a larger model lead to better results?
A larger model has more capacity to learn, so it can understand more detailed patterns and relationships in language.
Exactly. With more parameters, the model can represent and capture intricate language features, things like nuances, idioms, and subtle contexts that a smaller model might miss. They scaled the model up to 11 billion parameters, which showed significant improvement. However, they also noticed diminishing returns. After a point, adding more size brought smaller improvements. Why do you think that happens?
Maybe because the model already learned most of what it needed, and making it bigger doesn't add much unless there's more new data to learn from.
Precisely. Once the model reaches a certain level, it effectively captures what's in the data, and adding more capacity doesn't help much. It's similar to a student who's already mastered the material. More study might not lead to much more improvement. They also scaled up the dataset, increasing the amount of text used during pre-training. They found that scaling both the model and the data yielded the best results. Why is scaling both important rather than just one?
If you only scale the model without enough data, there won't be anything new for it to learn. But scaling both means the model can fully utilize its increased capacity.
Correct. A larger model needs diverse and expansive data to make full use of its capabilities. Scaling both ensures the model continues to be challenged and learns effectively. Moving on to 3.7. Results. The scaled models achieved state-of-the-art performance across several benchmarks, including tasks like question answering, summarization, and translation. This demonstrates that the combination of scaling, a well-chosen dataset, and effective training strategies significantly improved performance. Why is it important for a model to excel in multiple tasks?
It shows the model is versatile and has a deep understanding of language, not just one specific type of problem.
Exactly. If a model can perform well on a range of tasks, it means it has a broad understanding of language, making it much more useful across different scenarios. It proves that the model hasn't just memorized patterns, but understands underlying principles that apply to diverse tasks. The authors also observed patterns in how performance improved, called scaling laws. These laws helped predict how much the model would improve with more parameters or more data. Why might these scaling laws be helpful?
They make planning more efficient since researchers can predict the benefits of increasing model size or data, which helps allocate resources wisely.
Exactly. Predictable scaling laws help researchers decide the most effective use of resources, whether to invest in a larger model, better data, or more computation, making future model development more targeted and efficient. To sum up, the authors showed that scaling both the model and the data led to significant improvements. But they also pointed out that there are limits, with diminishing returns after a point. Their results highlight that thoughtful scaling, balancing model capacity with the right amount of data is key to achieving state-of-the-art performance. These findings provide a roadmap for building powerful NLP models. It's not only about making the models larger, but about understanding how to effectively match model capacity with data and training strategies to maximize performance. This thoughtful approach allows us to push the boundaries of what these models can do in practical, meaningful ways. Now let's discuss the reflections section of the paper. This is where the authors step back to consider the broader implications, challenges, and future directions of their work, like taking a moment after a journey to evaluate how far you've come and plan for what's next. The authors start by reflecting on the impact of the unified text-to-text approach. By treating all NLP tasks as input-to-output text transformations, they simplified the development process. Imagine using a single versatile tool for everything. That's what this framework aims to achieve. Why is this simplification important?
It makes the research process more efficient. If everyone uses one approach, they can focus on improving that instead of learning many different methods.
Exactly. Simplifying the framework means researchers can refine one flexible system, reducing complexity and speeding up improvements. It also makes sharing advances across tasks easier. They also address the trade-offs of scaling up. Larger models and more data improved performance but also increased computational costs, raising concerns about accessibility and environmental impact. Why are these issues significant?
Because if only big companies can afford it, the field becomes less open. Plus, the environmental cost is a big concern.
Absolutely. High computational demands mean fewer participants in AI research, and the environmental impact can be significant. Finding ways to make models efficient and accessible is key to addressing these challenges. They also reflect on the importance of data quality. They found that bigger models weren't always better. The quality of the dataset mattered a lot. Why might quality be more crucial than quantity?
High-quality data teaches the model useful patterns, while poor data could lead to learning irrelevant or wrong things.
Exactly. A large model trained on bad data learns bad information. Quality data helps the model develop a deeper and more useful understanding of language. Looking ahead, the authors mention the need for more efficient models, suggesting approaches like model distillation, where a large model is used to create a smaller one that retains most of its performance. How could this help address some of the concerns we discussed?
Smaller models mean more accessibility. They require less computing power, making them available to more people.
Exactly. Distillation helps create powerful yet compact models, reducing computational costs and making these technologies more widely accessible. Finally, the authors emphasize the importance of sharing. By sharing data, pre-trained models, and their methods, they enable others to build on their work, which accelerates progress in the entire field. Why is this openness beneficial?
It lets others save time and resources. Instead of starting from scratch, they can use existing models and focus on improvements.
Exactly. Sharing models and data allows researchers to build on each other's efforts, driving faster and more meaningful advancements. In summary, the reflection highlights the power of a unified approach, the need for balancing model complexity with efficiency, and the importance of high-quality data. The authors also stress the need for accessibility, sustainability, and collaboration in advancing NLP. This reminds us that AI progress isn't just about building bigger models. It's about responsible, collaborative development that ensures everyone can benefit from and contribute to advancements in technology. All right, that brings us to the end of today's discussion on T.5. We've seen how a unified text-to-text framework can make complex NLP tasks much more manageable and effective. I think it's safe to say that T.5 has set a new standard for versatility in language models.
Absolutely. And it seems like it's not just about the technology today, but also about how these unified approaches can simplify future research and application. I'm excited to see what comes next, maybe even more refined models that use less data and compute but are still powerful.
That's a great point. The future of NLP is definitely heading towards more efficient, accessible models, without compromising on performance. We might even see advancements in how these models understand and adapt to new tasks with minimal training. It's an exciting time to be following this field.
Definitely. Thanks to everyone who tuned in today. We hope you enjoyed exploring T5 as much as we did.
And thank you for being part of this journey with us. If you found this episode insightful, stay tuned for more fascinating explorations into the world of AI and NLP. Until next time, take care and keep learning.
Thanks for listening, everyone.